All right. Welcome to the Murray Amateur Radio Club. Sorry for the technical difficulties with the Zoom session. I will endeavor to fix that by next week, probably by disposing of all of the Zoom links existing and creating a new Zoom link for all club meetings, but we'll figure that out as we get closer. But all right, tonight we're going to talk about SWR. How many people have heard of SWR? Everybody's hand should go up. All right. Well, let's go ahead and see where we can go with this. So, what is SWR? SWR stands for Standing Wave Ratio. And what this is it is a measure of impedance matching of loads to the characteristic impedance of a transmission line or waveguide. Now, I realize that I just sounded like the adults on the Peanuts cartoons. Wah, 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 right? So we're going to talk about it. Yeah, this is an interesting concept. So what is it really? And I promise a little bit of math. I said no math, but
It's even
yes, just a tiny amount of math. A tiny amount of math will be coming up. It will be towards the end. So if you are averse to math, you're welcome to leave at that point. But I will tell you exactly when the math is going to start and exactly when the math is going to end. So be patient with me. There will not be a lot of math. There will be a tiny amount of math. Okay. There's plenty of math if you really want to learn how this stuff really works. Math is kind of cool because we use math to model real world things. And physicists, well, scientists in general, science falls into a few basic categories. Basically, if it stinks, it's chemistry. If it's green or it wiggles, it's biology. And if it doesn't work, it's physics. But that said, math helps us to model the physical world and understand how it works. So math is kind of important, but we're going to try to avoid it as much as we can. Okay. I know a lot of people are like, but they told me I would never need this algebra ever again. And they were mostly right. But there are cases where a little bit of math is good to learn. Okay, so first let's talk about what is a wave. So a wave is a physical phenomenon. I'm not talking about wave, like you see the people on the parade floats do. Well,
no, that's a
it's more like this, right? Oh, I'm waving. Yeah. A wave is a physical phenomenon, and it is a propagating dynamic disturbance in something. Okay. So you could have waves in water. Anybody been to the beach? You see the waves come rolling in on the beach. It could be in the air. Anybody hear the sound of my voice? That is a sound wave that I am generating. It could be radio frequency energy, which hopefully we all have some familiarity with. It could be light. There's a lot of things that take on the properties of waves. Now, when we start talking about electromagnetic radiation, it's kind of a wave and it's kind of a particle, and it depends on how you look at it. But in terms of what we want to talk about, we're going to talk about it in terms of waves, okay? So there's a couple of different types of waves that we're dealing with when we do radio stuff. The first is what we call a transverse wave, and that is what sound is, okay? It's basically a compression and refraction of pressure. Okay. And that's what this left hand image is kind of reflecting. There's all these particles here. They don't really go anywhere. They just kind of move back and forth a little bit. And the signal is carried through this medium without anything moving except the signal. Isn't that kind of cool, really, when you think about it? When I'm talking to you, I'm making air move with my mouth and my vocal cords, and the air that's leaving my mouth is not hitting your ears, but the energy coming from me is propagating through the air and reaching your ears and making your ears wiggle. And that's how you hear what I'm saying, Dan.
Is that why you can't hear anything in space?
Yes, there is no medium to carry that energy, so you can't hear. There's no sound in space. How many movies get that wrong? Almost all of them, right? There's very few that get that correct. But yes, yes, like the Enterprise, right? Yeah, because things moving fast have to make noise because that's what we're used to here on Earth, right? Electromagnetic. Another comment?
Beach, some movement there.
If you actually take a thing that is floating and you put it out in the water, you will observe that it sits there. It doesn't come into the shore. The wave energy comes into the shore, and the wave will break on the shore, and then the water will go back out. Then it'll come back in and go back out. It's the same water all the time. Yes, some water moves, and you will notice that eventually that float might move from the position where you left it. But in general, when you're watching a wave happening in water, that water is basically just moving up and down. It's not really moving back and forth at all. The wave is moving in a particular direction, typically towards the shore or away from whatever caused the wave. Think about it like when you throw a rock into a pond and there's a splash and then there's a ripple that goes out away from that in the circle, right? The water doesn't all leave that spot and now there's no water there, but the energy of the rock hitting the water, that energy travels away from that point. Does that make sense? Okay. Same thing happens with electromagnetic energy. And when we talk about electromagnetic energy, we talk about a longitudinal wave, where, as shown in this image on the right, the wave is kind of moving up and down. And as you watch the wave front, it progresses in a forward direction from one point to another point. Okay. The actual electromagnetic, whatever they are, that's making up that wave, that doesn't actually move. Just the fact that the energy is there, that energy pattern moves across. Okay. So waves are kind of cool. They do interesting things. All right. So waves carry energy and information. So when we work a radio, it works by modulating a wave in a particular way. And we talk about AM modulation or FM modulation. And in our diagram here, we have a signal, and then we either apply an AM modulation to it, an amplitude modulation, we affect the strength or the size of the wave, or we apply a frequency modulation to it and we affect the wavelength, the distance between the two peaks of each part of the wave as it moves along. In single sideband, it's the same as AM, except we only take half of that, right? We take either the upper sideband or the lower sideband, and we don't take the whole amplitude modulation wave. And in our radio, what happens is when we key up our radio and we talk into the microphone, we produce sound, right? That sound travels into the microphone and causes the microphone to wiggle, which generates an electric signal that varies in strength. And that signal travels into the radio, down the little microphone wire into the radio. And then the radio takes that signal and combines it with another signal generated by an oscillator and produces a radio frequency wave at a particular frequency. And then it sends that down the feed line and out to the antenna and out into space. Okay. The receiver does the opposite. It picks up those waves that come in, it decodes the information out of that signal that's coming in, masks off the frequencies that it's not interested in. So it's only decoding the particular frequency you want to receive. And then it takes the information out of that and converts it back into an audio signal using a speaker. The sound waves travel through the air and hit your ears, and you hear what the person on the other end of the radio is saying. Pretty simple stuff. We know how this works. We understand most of how this works, right? There may be some shortcuts depending on what you're doing. If you're doing any kind of digital stuff, you're converting the signal into a digital signal and then you're encoding that and sending that out on the air. If you're doing any kind of like Morse code, CW, you're just turning the signal on and off. You're not actually putting any modulation into it. It's either the presence of the signal or the absence of the signal that carries the information. But in general, that's how radio is working, right? All right. So the next concept that we have to talk about is impedance. Who knows what impedance is? Yes, you probably do. And I'm glad to see nobody else raise their hand because impedance is one of those weird things that we think we understand until we try to understand it. And then we realize we really have no idea what the heck is going on here. But it's really quite simple. Impedance is to alternating current or AC as resistance is to DC. So remember when we were talking in our electricity and electronics classes the last few weeks about resistance being something that makes it harder for energy to pass through it. Impedance does basically the same thing, but for an alternating current. Okay. It's measured in ohms, just like resistance is. And everything that we work with has some level of impedance. Now, when you're designing a circuit, you may assume that there is no impedance and design your circuit accordingly because ultimately it's going to work similarly and it's easier to do the math if you ignore the impedance. But there is impedance in everything, right? And in fact, if you look at your radio, you will note that on the output of the radio, the transmitter output that goes to the antenna, it'll say 50 ohms, typically in amateur radio radios. That's the impedance, the expected impedance from the source, the radio being the source. And so what you want is you want the entire system to be at that level of impedance. The 50 ohm impedance is what it's expecting. Now, if you ever work with cable TV stuff runs at 75 ohms of impedance. That's why we don't use cable TV cable for our feed line from our amateur radio to the antenna. The impedance doesn't match. 50 ohms versus 75 ohms. I see a lot of blank stares. Stan, go ahead.
Resistance is expressed as R. Reactance is expressed as X. Impedance is expressed as Z.
Okay, so
a combination of resistance and reactance produces impedance.
So resistance is R, reactance is X, and impedance is Z. So if you're looking at the math, those are the symbols that you would be using. We're not using, yeah, there is actually a real and an imaginary component of this stuff. We're not going to go into any of that, right? So when you start talking about imaginary numbers, people tend to get like, yeah, we're not going to do that. We're not going to go into that. But yeah, though there are, believe it or not, imaginary numbers. And you're thinking, aren't all numbers imaginary? But we talk about a number as being a complex number if it has both a real and an imaginary part. And you can do math on those just like you can on regular numbers. And it's too much to go into for this presentation. Yeah, I know, but like I said, no math, remember? So we're gonna not talk about that. But yeah, so hopefully your transmitter has 50 ohms of impedance, your feed line has 50 ohms of impedance, and hopefully your antenna has 50 ohms of impedance. Now, who's worked with ladder line feed line before? A few people. What's the impedance of ladder line? It depends. In amateur radio, what's the typical one? Bruce says 450 is typical, right? The antennas that you used to use on your FM radio is 300 typically, right? Notice that 300 is a multiple of 75. That's interesting, isn't it? We're not going to go down that road, but so what happens if there is an impedance mismatch? All right, so let's talk about what happens when we send a signal down some wire or some mechanism, and there's an impedance mismatch. What's going to happen is the signal will reflect off of that transition point between the two. Okay, so if you look at this diagram, it's showing an incident wave in red. The incident wave is the forward wave. We call it the forward signal or forward wave. And that wave is traveling from left to right. And when it hits that impedance mismatch location, some of that energy is going to bounce back. Now, in this diagram, all of it bounces back. We'll talk more about that in a minute. But what you're seeing here is the, what is that? Green or some kind of bluish, greenish color. I don't know what it is. Turquoise, sure. Okay, turquoise. The turquoise wave is the reflected wave that is coming back from that point. So the two waves are moving in opposite directions. So what happens when two waves are moving in opposite directions on the same medium, or even if you just have multiple waves on the same medium? Well, what happens is they either add to or subtract from each other. So you will see here, this is a situation where the blue wave is moving left to right, and the red wave is moving right to left. Can you guys see that?
Yeah.
Okay, it does look pretty good on there. Okay, good. And if you add or subtract those as they go past each other, you get this black wave effect. And this is called the standing wave. What do you notice about this standing wave? Look at the peak of the blue wave as it goes across. It's going across, right? How about the red wave? The peak is going across. What's happening to the peak of the black wave?
Yeah.
It's not going anywhere. It's just going up and down, right? So this is why we call it a standing wave. It's not moving, okay? It's not moving left or right along our medium that we're talking about. The other things that you will notice are these little red spots where there's nothing happening. Those are called nodes, okay? And then the opposite spots, or the spots in between the nodes, where it's either the highest or the lowest, those are called antinodes, okay? Just some terminology. Do we need to know that? I don't know if we need to know that. So let's talk about wave harmonics for a second. So if we've got our wave going across and we're running out what we call our first harmonic, the wave is the wavelength from peak to peak, or from center point to center point, or from valley to valley. It's going to be one wavelength long, okay? The harmonics are then going to be a fraction of that. So if the second harmonic is going to be 1/2 of a wavelength long, and that's where that node is going to end up. If you've got a third harmonic, you're going to end up with two nodes in the middle, plus the ones at either end, and the fourth harmonic likewise, and so on. It goes up and up and up. So why do we care about that? When you're trying to test your radio to see how well it's working, energy that your radio is putting out on the second, third, fourth harmonic is energy that's not going out on the first harmonic, right? It's not energy that is on the right frequency. It's going to be energy that's on the wrong frequency. And the FCC has specified that for a radio to pass whatever certification it needs to pass, it needs to put out less than some amount of radiation on these harmonics. So if your radio, like your friendly neighborhood Baofeng from 10 years ago, is putting out more energy on the fourth harmonic than it is on the main first harmonic, that's probably not good for you, right? That's wasting your energy. That's all I'm going to talk about wave harmonics. All right, so let's talk about properties of standing waves. Remember, we talked about how this wave just kind of sits here and bobs up and down, right? It doesn't actually move left and right. So it has an amplitude, and different points along that wave, the amplitude is going to go up and down as this wave goes up and down, right? And again, we have the nodes and the antinodes. One thing to think about is this standing wave, instead of transmitting the power, it's essentially storing that power temporarily, right? As it builds up its amplitude, and think of the amplitude or the height of the wave as the amount of power in the wave. So as it goes up, it's got more power in it. As it goes down, it's got less power in it, okay? So that is going to be part of our problem with standing waves. One other thing to note is the distance between two nodes is half of a wavelength. So if we look at that, let me turn my pointer on real quick. You can see here, this is one wavelength, right? So there's a node halfway along this wave, and then there's a node another halfway along this wave. So that's something to understand. Again, we're probably not going to care about that because we're not going to get into the math too much, but it is a factor that comes into play when you're working with standing waves. All right. So let's go back to our impedance mismatch. So in our impedance mismatch, some of the energy is being reflected back. Now, in this case, not all of the energy is being reflected back. Some of the energy is being reflected back. So the returning wave front is not going to be as big as or as powerful as the forward wave. Does that make sense? I'm putting a certain amount of power into my wave and sending it down the line. Some is coming back. If all of it comes back, then my signal is not going anywhere, right? Except right back at me. We'll talk about that in a sec. Yeah, we'll talk about that in a sec. So some fraction of it, depending on how bad the impedance mismatch is going to be coming back. And so what happens is, if we look at this chart here, this one is almost all of it is coming back. And so you can see the nodes are not all the way at zero. There's still some information there, right? There's still some energy there. The closer to all of the energy coming back, the closer I get to nodes that are right at the 0 point. Okay. If we think of this as positive and this is negative, these will be right at the 0 point. And so this is probably more accurate as we think about in our standing wave, what it looks like as the energy is coming back down my wire. Okay. So I'm going to warn you, there is math on this next slide. Okay. So let's go back to SWR. So the standing wave ratio is the ratio of the forward power and the reflected power. This is the beginning and the end of the math in this presentation. Okay. It's all right here in this one formula. And if you look at this formula, let's decode this for a second. So we have PR, no, sorry. PR, that's the power reflected. And PF, that's the power forward. That's the power we're sending. This is the power that's coming back. And we take those and we divide them and we get some number. We take the square root of that and then we add it to 1. We do the same thing here and we subtract it from 1. And that gives us our SWR number. Okay. End of math. That's it. We're not talking about math anymore. All right. So how do we measure this? How do we know what our SWR is? Well, there's a device. Look at that. It's called an SWR meter. You have one of these in between your, look at that. Al brought one for us. Brought a couple of them for us. You want to pass those around so people can see them? Hello? Is this the person to whom I am speaking? Sorry. So what you got on here, there's a couple of scales, okay? And there's a couple of needles on these scales. And these scales are basically just showing you the forward power, and on here it's in watts, okay? And the reflected power, and it's also measured in watts. So what happens is, as you transmit, this needle will come up to a certain point depending on how much forward power you are applying. And this needle will come up specifying how much reflected power there is. And where those two needles cross, which will be somewhere in this region, it will hit one of these lines or be close to one of these lines. And these lines will tell you what the SWR number is for what's happening right now. Okay? The first time I saw one of these meters, I was like, what in the world is this thing? But how does this work? Once you understand what's actually happening, some energy is going down the wire, some energy is coming back. The amount that's coming back versus the amount that's going forward defines this standing wave ratio, or SWR, okay? There's some knobs and buttons on here that tell you different things, but we don't care about that in regards to what we're talking about. But basically, this is going to give you your SWR on this red range. So where these two needles cross, that's going to be somewhere along one of these paths, and that will tell you what your SWR is. Isn't that cool? That's like super cool when you think about it. I don't know when this meter was invented, but way before we did any digital stuff. This thing has been around for a long time. And when you start thinking about the physics behind this and how it works, it's really quite cool. Okay. What's another way that I can tell what's going on in my antenna system? Nowadays, we have these cool things called the nano VNA. You guys ever heard of a nano VNA or a VNA in general? Look, Alan brought a VNA. Look at that. So what this thing does, a VNA is a vector network analyzer. And so that's a lot of words that mean basically it tells you a picture visually what your antenna is doing. Okay. And this thing on here, I'm going to talk about this diagram that's on here in just a second. I'm not going to talk about it a lot because that starts getting you back into math. And remember, I said we're not going to do any math, right? So just bear with me. We'll talk about that in a second. But this little gizmo, you put this in your signal, in your system, so you have energy coming in, you have energy going out to your antenna, and this will actually tell you how things are in your network, your antenna system. Oh, you can turn it on. It's burned. Oh well. Okay. Anyway, so this is a pretty cool little gadget, and you can actually get one of these pretty darn cheap nowadays. I've got one that's a little bit smaller than Alan's, but they're really not that expensive. Once you understand what's happening and how it works, it actually gives you some really useful information. Until you know that, it's just a box with lights on it that you have no idea what's happening, right? So you need to understand the math behind it and figure out what's actually going on. But it is, and I'm gonna mention Smith charts right at the end of the presentation, in the context of saying I'm not going to talk about Smith charts. But yeah, so a nano VNA is a pretty cool gadget. It's not as simple or analog as the SWR meter, but it performs similar functions and gives you more information at the same time. Okay. So why do we care about SWR? Why is this a big deal? Why do we even have this meter to measure this thing, right? What does it do? Remember, what we're talking about, there's a couple of things, right? When I'm transmitting with a certain amount of power, that reflected power has to go somewhere. Where does it go? It goes into my radio and into the amplifier that's trying to send the signal out. So it's essentially causing back pressure in my transmitter. And what happens to energy that you're not using? What does it turn into? Heat, right? What happens if you take some electronics and get them very, very hot? They stop being electronics and they start being rocks, right? So yeah, once the magic smoke comes out, it's really hard to get that magic smoke back into the tiny little piece of silicone. So reflected power, again, is power that doesn't go out your antenna, so it's wasted. And it's power that comes back into your radio, which is where it's wasted as heat inside your radio, where you don't want extra heat. You've already got enough heat from the amplifier circuitry and everything else that's going on in there. So we want to minimize our SWR, right? That would be something that would be pretty good to do, right? If we can make our SWR close to 1, which would be all of our power is going out and none is being reflected, that's great, right? That's what we want. Now, in practice, are we going to get there? You can get pretty close, depending on what you do. So what do we do about it? Well, there's a couple of different options. The first option is to make sure that your impedance matches across the entire system. So not only your transmitter, your antenna, your feed line, everything is matching and there's no place to waste any energy to reflect any signals back. Now, how do you do that? What's one way you can do that? Make sure your antenna is exactly the right length for the frequency you're transmitting on. Okay? That will help you get really close to where you want to be. That's great if you only ever transmit on one frequency. Do we ever change frequencies and transmit on a different frequency? Why would we ever do that, right? Why would you need to change frequencies? You've got a frequency, use it. Well, if you're talking about broadcast power like KSL radio, yeah, they're going to have their antenna system tuned to the exact frequency they're transmitting on because they're only allowed to transmit on that one frequency. And they're also putting 10,000 plus watts into that system. So they're putting a lot of energy in there. They want it to go out the antenna. So they want that all to be tuned perfectly. When we're doing amateur radio operations, we want to be able to change frequencies. Maybe we want to change bands entirely. Maybe we want to, do all kinds of crazy stuff like, I don't know, bounce signals off the moon or something. I don't know. We do weird stuff in amateur radio. But the main thing is you want your antenna system to be tuned to be as close to the frequency that you're transmitting on as possible. Now, when we do that, one way to do that is make sure your antenna is as close to the frequency you want to use as possible. So if you've got a 20-meter band that you're transmitting on, and you've got an antenna that's tuned to about the middle of the 20-meter band, that gives you the best tuning that you can get out of that, essentially, right? You're going to get, you're not going to be too far away from the center wherever you go within that band. So you can do that. The second option, it's really painful when you have to run out and trim your antenna every time you want to change frequencies. So the second option is to use a device called an antenna tuner, which is kind of a misnomer because it doesn't really tune the antenna. What it does is it tunes the impedance of the system, not just the antenna, but the entire radio feed line antenna system. What it does is it combines inductors and capacitors to make the impedance match as close as possible. Now, how many people have heard of people using impromptu antennas like a rain gutter, for example? Just clamp your transmitter to the rain gutter and start talking. That's okay. You can do that. You better have a good antenna tuner because the SWR is probably going to be crazy on something like that. You have no idea how long your rain gutter is, what the properties of the metal that it's made out of are. All of those things go together to cause this impedance mismatch. So you better have a good antenna tuner. Now, what happens with an antenna tuner? Is it perfect? Does it solve all of our problems? Well, it still wastes some energy, okay? But it wastes it inside the antenna tuner, not in the transmitter of your radio system. And the antenna tuner is designed with components that are beefy enough to handle that waste energy without melting down or burning up, okay? So it's a good idea to have an antenna tuner. Dan, you have a comment?
Yeah.
Oh, Dan first, and then I'll come to you, Stan.
So it's very important to understand that the antenna tuner, a bad antenna is still a bad antenna.
Yes.
If it's mistuned, if it's not resonant, you're still not getting the FARs that you think.
The FARs.
Yeah.
Somebody who's been watching Not a Rubicon, I think.
So people think that their antenna tuner fixes the impedance mismatch, and they still wonder why they can't talk to Africa.
Yeah. So Dan's comment is, even if you're using an antenna tuner, it's not a magic device. It's not going to magically make all of your energy go out of the antenna, right? What it's going to do is prevent too much energy from coming back into your transmitter by preventing that, matching that at the antenna tuner side and not inside your transmitter, okay? So even though it says, hey, I've got a great SWR now with my antenna tuner in place, as far as it's measured at the transmitter, If I'm measuring my SWR out at the antenna, it's probably still bad, right? If the antenna is bad, you're going to have problems. You're not going to get all the energy out the antenna that you want. So having a well-tuned antenna is still a good idea. And that's why you don't take a 40-meter antenna and use it on 15 meters. You can use a 40-meter antenna on 20 meters and on 80 meters mostly because they're pretty close when you look at the harmonics. Remember we talked about the harmonics before? They're pretty close. But you need to be aware if you're on a frequency that isn't, or a band that isn't a harmonic of that antenna, that's going to cause you problems. We talk about our tri-band radios, especially in Murray Amateur Radio Club, because our repeater is on the 220 band, right? The 1.25 meter band. Now, when you buy a dual band handheld and it's got a nice antenna that comes with it, a dual band antenna, that works because the 70 centimeter band and the 2 meter band are harmonics of each other. Okay. So one antenna will work pretty well, not perfectly, but pretty well on both bands. When you start folding the 1.25 meter band in there, it's not a harmonic with either of those other two. It's actually a harmonic with, what is it, the 1.8 meter band or something like that? No, there's what was the band before the 2.5 meter band? That was the one that we had before we got 2 meters. It's actually a pretty good harmonic of that, but not of the 2 meter or the 70 centimeter. So if you've got a tri-band antenna, it's actually got some matching circuitry in there to prevent high SWR from coming back into your handheld or your mobile radio. Okay. The antenna is specifically designed to handle the multiple bands. All right. So antenna tuner, pretty good device, keeps you from burning up your transmitter. Not perfect. It's not going to solve your problem and allow any piece of material to do whatever you want it to do. Will it antenna? Maybe. But will it be good? Probably not. Okay. Let's see. So what SWR do we want? Ideally, we want 1-to-1. That's the perfect match. Okay. It will be perfect. It will be every piece of energy that I put into it will come out the antenna. We're not going to run into that. In reality, SWRs up to 1.5 are probably fine. Even SWRs up to 2 are probably okay. Your radio can probably handle that. If it's worse than that, there's a couple things you can do. Don't transmit as much as you can avoid it. Keep your transmissions really short. You're still wasting energy, but you're not going to burn up your transmitter if your transmissions are very short. It can probably handle that power coming back in for a very brief period of time. Also, reduce your transmit power. If your radio is designed to transmit at 100 watts, drop it down to 10 watts. It can probably handle a much higher SWR at 10 watts than it could at 100 watts. Okay. If your circuit is open, that's basically the antenna is not connected. Or if there's a short circuit, that results in an infinite SWR. All of the power that you send out comes back. Okay. And that's what we were talking about, that ideal standing wave where everything that I send out was reflected back. My return wave was the same strength as my transmitted wave. That's considered to be an infinite SWR, and that's infinitely bad for your radio, okay? And no signal is going to go anywhere. So this is why they always tell you, don't ever transmit without an antenna attached to your radio. Because if you do, all of that power is going to stay in the radio. And if you've got a broken antenna or damaged feed line or something like that, that causes a short circuit, that's just as bad as not having an antenna at all. Okay? So keep those things in mind. All right. For future research, if you're interested, learn the math. There's a lot of great resources online that explain how the math works. They're pretty good. You don't have to be a mathematician to follow this stuff. It's not that complicated. And there's also this thing called the Smith chart, which you can use to graphically figure out what your SWR is and how it changes based on your frequency and based on the properties of your antenna system. And that's basically what that nano VNA device will do for you, is produce this information. So if you have one of those, you don't have to do it by hand. Learn how to do it by hand. It's actually not that hard to do. And once you understand what's going on, you will have a whole new realization of what your antenna tuner is doing for you and what it's not doing for you. Okay. All right. I said it was going to be short. That's all I got. So this could have been another hour if I wanted to go into the math, but I'm not doing that. We're going to call it right here, and we're going to say, give me your comments. Dan, go ahead.
Say, as soon as you do that Smith chart, you do a lot of math.
Yeah, there's a lot of math on that, right? It's good to learn how to do that math. It really is. It will help you as you design your antennas and want to build an antenna system that will support your radios and the frequencies that you're operating on. Dan, you had a comment as well.
Yeah, there's people here who would like to actually get involved with doing this stuff, so that's what I would like to do now.
Okay, so we have some stuff right here, and Alan brought a bunch of stuff. If you want to hook this stuff up and see what happens, I'm going to go ahead and end the Zoom at this point.
Hey, I got a question. Can I ask one before we wrap it?
Yeah, go ahead, Justin.
So my understanding is antenna tuners are not only to protect your transmitter. I think, aren't they supposed to also take your kind of reflected wave and reflect it back to the antenna?
Not as far as I'm aware.
I think
don't think
that's something we need to look up. I don't think they're just dissipating the heat themselves instead of inside your radio. I think, obviously they're gonna soak up some energy just being in the path, but I think that their combination of capacitors and inductors attempt to reflect it back towards the antenna.
Even if it did, it would be out of phase with your original signal, and it
Well,
would probably be more harmful than helpful.
No, that's the whole point. Is it puts it in phase with the original signal. That's what they're doing. Is they're taking that reflected signal and realigning it to the same phase as the transmitted signal.
I see Stan scowling over here. Maybe, do you want to come up and talk in the microphone so that they can hear?
I just want to say, actually, Dan said the word, and the word is resonant. And that antenna isn't resonant because it's the right length, as you mentioned earlier, then you got big trouble, and that's what the SWR is all about. But there is such a thing as a base load, base tuned antenna. And that's another subject, so I'm not sure where exactly he's going with that.
So Stan's comment for the recording and the people on the Zoom is that it comes down to the antenna system being resonant. The lack of resonance with the particular frequency that you're using is what's causing this SWR, or this return frequency, this impedance mismatch.
Sure. Obviously, if there's no return signal, you don't need an antenna tuner at all. But what I'm saying is, if your antenna is not perfect and it's reflecting some of your signal back, the antenna tuner, in my understanding, is then going to take that reflected signal and reflect it right back towards the antenna. I mean, it's not ideal because, like coax feedline, you're going to lose a lot of your energy bouncing back and forth along that coax. I mean, you don't want to do that because you're just wasting energy, running back and forth along the cable. But my understanding is that it's trying to send the energy back down the cable and not just burn it up internally.
Yeah, I have never heard that before, but I'd have to do some research on that. We can talk more about resonant antennas when we do some antenna building projects, and we probably should do that because those are factors that come into play when you're measuring how long the elements of your antenna are and things like that. And I think we've got that scheduled for a future meeting. So I'm not sure when that is set up. Maybe Russ can tell us if he's still here.
Yes, I can look that up, but I just looked up Justin's question, and it says, yes, an antenna tuner or antenna tuning unit reflects power back towards the antenna, does not tune the antenna itself, but rather matches the antenna system's impedance to the radio, taking reflected energy from the feed line and reflecting it back toward the antenna, allowing the transmitter to see the proper load. So
I'm gonna have to read up on the physics of the antenna tuner to understand that a little better, but I will definitely do that and bring results back to the club at a later date.
I don't know if you guys have any. I don't know, but they're supposed to be like capacitors and inductors. My guess is there's not like big resistors and heat sinks in them. I don't know. I've never really seen a standalone antenna tuner, but
It makes little difference what happens to the FARs on the other side of the tuner. What you don't want, that antenna tuner is preventing that standing wave to be hitting your radio, right? It's like the firewall.
well, I guess what I'm saying is that's not the only reason, because some of it will make it back to the antenna, right? It ought to make a difference in the bars. I mean, look. I mean, coax feed line is very, very lossy. So sending a signal back and forth, you're going to probably lose it all in your coax if it's very long. But it should be sending it back. It shouldn't just be burning it off, and there should be some measurable difference other than just not frying your radio.
There may be some of that, but that's beyond this class today.
I'll look into it, Justin, and see what I
All
can find out, and maybe we can find some better resources that explain that in a way that we can all understand. But I know Stan is sitting here shaking his head, and he's the closest we have to an RF expert. So,
Well, don't get me wrong. I'm not saying it will fix.
no, I'm not saying you're saying that. I'm just saying
Okay.
I hadn't heard of that, and I don't think anybody else here has heard of that. But if that's, I mean, like Russ went and read it, as far as I know, I'm not disputing it. I'm just saying that I hadn't heard of that factor before. So
I'm not disputing it, but I also think it's a moot point in reference to the antenna tuner, why you want to use it.
So-
You're not gaining anything by,
it's not increasing the amount of signal that gets out of the antenna. It's
Yes,
basically what
okay.
you're saying.
it's still a bad
Well,
antenna.
I'm kind of a noob, so I'll do some reading. I just thought that, but so don't take my word for it. Obviously, I'm the
right,
most
well,
biggest noob of
let's-
anybody. but
let's
I'll do some
research it.
reading.
It's worth pursuing.
Yeah, let's research it because I'd like to understand it.
Yeah.
That's why we have these classes, is to help us learn and understand things. And that's something that I had not heard. So I'm going to research it and see what I can find out about it. Any other questions or comments? Vern?
I've got a real basic question, simple mind. Is that a logarithmic or a linear scale? Or when you're talking about SWR numbers?
It's linear.
It's linear, yeah, I believe.
So 3 out of doesn't sound like much of a problem.
Well, it's not like if I put 100 watts out, I'm going to get 3 back. That's not how the ratio works, right? So essentially, if it's 3, it says I'm getting like a third of my energy back.
So that
It's,
logarithmic.
It's an inverse.
that is loosely translated, okay? That 3 does not mean.
Yeah, it's not literally 3 times, right?
Yeah, we say in those terms so we understand it. I mean, a 2 to 1 is like, that's a 1.5, I think is 75 ohm. And we get a lot of 75 ohm returns, antennas that are, if you get a 1.5 SWR, that's actually a 75 ohm impedance difference. So there's a 25 ohm impedance difference. And so a 3 to 1, it's and it's probably a dB thing.
There is, yeah, and dB is a logarithmic scale, right? So,
Yeah.
or an exponential scale. Sorry.
I think there's a side of that where it's logarithmic, because when we're dealing with dBs, that's exactly what we're doing.
I was thinking in terms of a loudspeaker system. Your speakers usually rated 4 ohm to 8 ohm to 16 ohm.
Right.
And your amplifiers are just in watts, and you just dump the power, and no one ever cared about it back then. The high-fidelity system.
You did when you're running 2 ohm speakers and you got 1,500 watts.
Yeah.
Yes, you do worry about it.
Yeah. Big numbers, Paul.
Well, that's a characteristic of impedance at a certain frequency, that 8 ohms. That's not 8 ohms measured with an ohm meter.
Right.
All right.
Yeah.
So it sounds like we've got more research to do and another class coming up. So I'm going to do some research. Justin's going to do some research, and we'll see what we can figure out. Stan also says he'll do some research. We'll see what we can figure out. I'm going to go ahead and terminate the recording, and then I'm going to point the camera over at Dan's setup here so people on the Zoom can see it if they want to see it. But thanks, everybody. I'm going to go ahead and stop the recording now.